So on the 1.4 worksheet, we're going to be talking about slope and area on different motion graphs. And on this first worksheet, we're really going to be relying on the slope equation at the top of the page here, which takes into account the rise and the run between 2 points. And so on the first problem, we've got 1 point at 0 seconds and 0 meters. And then the other point is at 10 seconds and 10 meters. And so in order to calculate the slope, first we need to find the difference in the positions, which is the numerator. The final position is 10 and the initial position is 0, and then find the difference in times, which is 10 seconds and 0 seconds. When we find these two differences, we get a fraction that's 10 meters over 10 seconds. And so what we can do is we can simplify the 10 divided by 10 into 1, and we can simplify the meters over seconds into 1 unit, which is meters per second, which is the unit of velocity. And so it's very important that we have this velocity that the object is moving at, but we also have to know what time is it moving at this velocity. And since this graph starts at 0 seconds and goes all the way to 10 seconds, the velocity of 1 meter per second starts at 0 and goes all the way to 10 seconds. And so when we're trying to plot that on the velocity time graph, we have to find where 1 meter per second would be, which would be right here. And then we have to plot that from 0 seconds, which is at the start of the graph, all the way over to 10 seconds over here. And so the resultant graph is this one, which is consistent the entire time because the slope in number 1 never changes. For number 2, we have 3 distinct slopes. And so we have a slope for the first 2 seconds, which is a steep negative slope. Then we have a slope that is horizontal for the next 3 seconds, and then we have a positive, less steep slope for the last 5 seconds. And so each one of these sections of the position time graph needs its own slope calculation. We can't just look at the first and final points, but we have to look at each second, at each section distinctly. And so the slope for the first section is -4 meters per second, and that goes from 0 seconds to 2 seconds. So we can actually plot that on our velocity time graph. We can go and find where -4 would be on the velocity axis, and then we can go from 0 seconds over to 2 seconds. Then the second slope is going to be 0, and that's because the initial position and the final position is 2 meters, and so it doesn't move. It has no displacement over this time period. And so for those 3 seconds, we've got a velocity of 0, which is going to be right in the middle of the velocity time graph. Again, we're not starting at the beginning, though. We already have information for that time period. We're starting at 2 seconds, and we're going to 5 seconds. And so this would be our graph in the middle. And then the final section, we've got a slope of positive 0.8 meters per second. And so that's going to be just under 1 right here. And that slope lasts from 5 seconds to 10 seconds. And so we're going to start it at 5 and go all the way to 10. And so our final graph looks like this. It's got 3 sections. Each section corresponds to one of the distinct slopes in the position time graph. For the next problem, we've got 3 distinct sections, just like the last one. And so each one deserves its own slope calculation, and then that slope will be transferred onto the velocity time graph. So we've got a positive 5 slope for the first 2 seconds. That's up here. Then we have a -4/3 or 1.3 slope for a section of 3 seconds. And then we have a 0 slope at the end for the last 5 seconds. And so again, each slope on the position time graph has its own section. Notice that the amount of time each section takes up is the same in both graphs. So this first red section, it only takes up 2 seconds. It goes from 0 seconds to 2 seconds on the position time graph. And then this line on the velocity time graph also goes from 0 to 2 seconds. Then the same can be said about the next section. The next section is 3 seconds long, and so this section is 3 seconds long. And so that's one way that we can make sure that what we're graphing on our velocity time graph matches the motion that our position time graph is communicating. On the next page and a half, we're going to be using a different equation, and this equation is to calculate the area of a rectangle. You can either use length times width, or the way that these are oriented, it might be better to consider this like width times height. And so what we need to do is we have to find the area of each of these rectangles created by our velocity time graph and the time axis. And then when we find the area of these rectangles, that area is equal to the displacement. And so in this first example, we have 10 seconds, which is the length. And then the height of this is 4 meters per second, and that's due to the scale. Each tick mark is 2 meters. And so then if we multiply those two, we find the product. We get a displacement of positive 40 meters. And then the distance is going to be the absolute value of that displacement, which gives us a distance of 40 meters. Notice that even though positive 40 with a plus sign or without a plus sign, they mean the same thing in math. In physics, this top one has a direction, and then this bottom one, this distance, does not have a direction. It doesn't have a plus or minus direction associated with it. The next problem has a length, or a width, I should say, a width of 10 seconds and a height of -7 meters per second. And that's one somewhat bizarre thing that doesn't happen in geometry, but it does happen in physics, that if the velocity is a negative velocity, then that actually can make the area calculated by this rectangle a negative area, which just means that the object moved to the left. It had a negative displacement. So when we multiply 10 times -7, we get a displacement of -70 meters, and then the distance will be the absolute value of that again, which this will look very different because when you take the absolute value of a negative, it becomes mathematically different, as well as in physics now that 70 meters for distance no longer has a direction like the displacement does, which is negative. In the next two problems, we have different velocities, and so what we need to do is we have to separate these graphs into separate rectangles and then find the area of each rectangle and add those areas up to find our displacement. So for this first rectangle, the width is 6 seconds, and then the height is 3 meters per second. For the area of that, we would multiply them and get positive 18 meters. Then when we are looking at our second rectangle, the width is 4 seconds, and then the height would be positive 8 meters per second. And so when we multiply those together, we get a product of positive 32 meters. And so our total displacement will be the displacement for the first 6 seconds plus the displacement of the second 4 seconds, which gets us a total of a positive 42 meters. Our distance is going to be the absolute value of each of these sections separately and then combined. But because this object didn't change direction, our distance is the same magnitude as our displacement. So the absolute value is 42 meters for distance. For number 7, we'll do the same thing by splitting this up into two rectangles. And so the total displacement is the sum of those areas, which is not positive 8 or 38, it is negative 38. And then the absolute value of that would be 38 meters. That's looking at negative 24 meters in this first rectangle, and then an additional negative 14 meters in the second rectangle. In number 8, we have 3 distinct sections, and so we'll do this the same way, but when we have to calculate distance, our approach will be a little bit more obvious because of the change in direction. And so if we look at this first rectangle, we can see that it has a width of 4 seconds and a height of -2 meters per second. Excuse me, -4 meters per second. And so when we multiply those, we get an area of -16 meters. We can then repeat that process for the second and third rectangles. And so the second rectangle has an area of +24 meters. And the third rectangle has an area of -8 meters. So to find the displacement, we'll just add these three distinct displacements up together. We'll find the sum of those three, and we get a total displacement of 0 meters. But we can't just take the absolute value of this total displacement. What we need to do instead is we need to find the displacement of each section by itself and then find the sum of those. So to do that, we'll have +16 plus +24 plus +8 and get a total distance of 48 meters. For number 9, we have a similar process. We've got 3 distinct rectangles that we need to find the areas of. And after we find these areas, we can find the total displacement by adding the areas together, which we get a +22 meter displacement. And then we need to look at each of these chunks separately, find the absolute value of them, and then sum those absolute values to get a distance of 46 meters. For number 10 and 11, the difference is that now we're only looking at a specific time period. And so what that does to our rectangles is it shortens their widths, because we're no longer looking all the way from 0 seconds to 10 seconds. Instead, what we're doing is we're looking from 2 seconds to 4 for this first rectangle. The middle rectangle stays the same as in problem 8, but then the last rectangle gets cut off at 9 seconds instead of at 10 seconds. So this affects the size of these rectangles, and therefore it affects the size of the total displacement. So we now have a total displacement of +12 meters. But then finding the distance is the same as it was before, where we're taking the absolute value of each of these sections and then finding the sum of those absolute values to get a total distance of 36 meters. And then number 11 is similar. Instead of looking from 2 seconds to 9, we're looking from 3 seconds over to 8 seconds. And so again, our rectangles on the left and right side of this graph are cut a little bit shorter than they were in question 9. And so our displacement becomes different because the area of the shaded region is also different. And we get a total displacement of +18 meters and a total distance of 26 meters. And the last two questions ask, looking back at these velocity time graphs, what type of motion result in the distance and the displacement being the same magnitude or the same size? And so as we look at this page, all of these 4 problems have the same sized displacement and distance. So we look at like +40 meters and 40 meters are the same size number, just like -70 meters and 70 meters. Even though one is has a direction to the left and one doesn't have a direction, they're still the same size. And so all 4 of these problems have the same size, displacement, and distance, and that's because the object always has the same direction of motion. So in number 4, the object is moving to the right the entire time. In object 5, it's moving to the left the entire time. But even in number 6 and 7, when the speed of the object changes, in number 6, the speed changes, but the velocity is always positive. So it's always moving to the right. And in 7, the speed changes again, but the object's always moving to the left. It always has a negative velocity. And so therefore, the claim for when motion or for what type of motion results in distance and displacement being the same size is when the object doesn't change directions, when it stays moving in the same direction the entire time. And those 4 graphs that we're looking at, numbers 4 through 7, are proof of, or are evidence to support this claim. 13 asks exact opposite. It asks us what type of motion results in distance and displacement being different sizes or different magnitudes. And so for that, we can look at numbers 8 and 9, and we can see that these distance and displacements are very different, not only in one has a direction and one doesn't, but they're different numbers. 0 and 48 are not the same size, and 22 and 46 are not the same size. And so that is because in both of these problems, the object changes direction. In number 8, it starts going to the left, then goes to the right, and then goes to the left again. Where in number 9, the object starts going to the right, it changes speed, and then it starts going to the left at the end. And when they change direction, that's when we start to have positive and negative displacements, that when we find the absolute value of them calculating the distance, that starts to make that number different than our displacement. And so, number 13, the claim of what type of motion results in distance and displacement being different sizes is when an object changes directions. And then those numbers 8, 9, and then 10 and 11, which are just modified versions of those, they all have an object that changes direction, and therefore their distance and displacement numbers are different magnitudes. Thank you very much for watching.